Let's kick things off today with a riddle. And honestly, it's one that humbles even the absolute smartest programmers out there. In this explainer, we're going to uncover the hidden force that dictates exactly how fast your machines run. Spoiler alert, it is probably not what you think it is.
So here's the central mystery. Imagine you write two tiny programs. They do the exact same math. We're talking 16,777,216 additions, to be completely precise. They operate on the exact same data, and they're running on the exact same chip. But when you hit run, program A finishes in an absolute blink of an eye. Program B, though, it just crawls. It literally takes over 7 times longer. If they're doing identical arithmetic to reach the exact same answer, where on earth did all that extra time go?
Well, the answer to that riddle? It's all about how they move. See, program A finishes instantly because it walks through your memory smoothly, totally in order. Program B, it takes 7.2 times longer, purely because it jumps around. And here's the kicker. During all that extra time, your processor isn't actually calculating anything at all. It's just sitting there, waiting. This kind of forces us to completely shift our mental model. We've really got to stop thinking of computers primarily as these giant calculators and start thinking of them as data movers. Which brings us to part 1, the physics of waiting. Why distance is literally time. For decades, right, processor speeds have just sprinted ahead, getting exponentially faster, while main memory speeds, well, they barely budged. This created what we call the memory wall. To really understand why memory is so slow, you have to look at physics. As the legendary computer scientist Grace Hopper famously pointed out, an electrical signal can only travel about 18 to 30 centimeters in a single nanosecond. So today, fetching a number from main memory takes about 60 to 100 nanoseconds simply because of the physical distance the signal has to travel across the motherboard. Picture a superhuman chef, okay? She can chop an onion in a microsecond, but the onions are kept at a grocery store all the way across town. Her chopping speed doesn't even matter at that point. Her entire day is governed by the commute. And that commute? That's your processor waiting for memory. And this brilliantly illustrates the ultimate engineering compromise we're forced to make to combat that distance. We basically have 2 ways to store bits. First, we have SRAM. It uses 6 tiny transistors. It's basically a light switch. Flick it on and it holds its state forever. It is incredibly fast, but it's bulky and it's wildly expensive. Then we have DRAM. It uses just 1 transistor and 1 tiny capacitor. It's super cheap, which means we can pack billions of them onto a single chip. But it acts like a leaking bucket. It is constantly losing its electric charge. So, because we literally can't afford a giant memory made entirely of SRAM, we're forced to build our massive, slow main memory out of those cheap, leaky DRAM buckets and just use tiny amounts of that expensive SRAM right close to the processor as our ultra-fast cache. Now, because our main memory is built from billions of these leaking buckets, there is a massive hidden tax. Every single cell in your computer's main memory must be forcefully refreshed every 64 milliseconds before it literally fades to nothing. And here's the crazy part. While a section of memory is being refreshed, the processor can't read it at all. It just has to sit there and wait. Okay, part 2, the 64-byte carton. Because memory doesn't move in single pieces. So how does this slow memory actually arrive when we finally ask for it? Well, it turns out it doesn't travel alone. This is arguably the single most useful fact in this entire explainer. Memory never, ever moves 1 byte at a time. It always moves in fixed 64-byte chunks called cache lines. Whether your program asks for 1 tiny byte or all 64 bytes, the hardware physically hauls an entire 64-byte block from main memory straight into that fast cache. Think of it like buying eggs. If a recipe needs 1 egg, but the store only sells cartons of 12, driving all the way to the store for a single egg and throwing the rest away is a massive waste of effort, right? When your program walks through memory in order, 0% of that cache line is wasted. But when it jumps around with a stride, pulling in 64 bytes just to use 1 and immediately discarding the rest, you waste roughly 88% of the data you just waited 100 nanoseconds to get. And this perfectly solves our opening riddle. Program B wasted its egg cartons. That is exactly why strided programs run 7.2 times slower on CPUs and often over 10 times slower on GPUs. But, this 64-byte physical rule is totally a double-edged sword. It rewards you for keeping data close together, sure, but it introduces the stealthy trap called false sharing. Imagine 2 separate processor cores working on completely different variables. If those variables just happen to sit next to each other inside the exact same 64-byte cache line, Well, every time one core updates its variable, it forcefully invalidates the entire cache line for the other core. So they end up playing this highly destructive game of ping pong, constantly overriding each other's memory drawers, thousands of times a second. It causes massive, completely invisible slowdowns.
Moving on to part 3, hiding the wait, making slow things happen at the exact same time.
Since we can't make that 100 nanosecond wait disappear, thanks laws of physics, we just have to hide it. Let's look at how modern computers actually pull off this magic trick. The secret is memory-level parallelism. Think about boiling a kettle. You don't just stand there staring at it for 3 minutes, right? You overlap your tasks. You butter the toast, you crack the eggs, you get the mugs ready, all while the water's heating up. Processors do exactly this. They don't fire off one memory request and just sit around waiting. They fire off dozens or even hundreds at once. So all those long 100 nanosecond wait times just overlap perfectly.
We can actually calculate exactly what it takes to hide this wait using a math principle called Little's Law. Now, don't worry, it's really simple in practice. Take a look at a typical graphics card, like an RTX 3060. It has this massive memory pipe that can deliver 360 gigabytes every single second. But because of that 100 nanosecond distance delay we talked about, to actually keep that massive pipe full, the GPU needs roughly 560 memory requests in flight at every single instant. This is exactly why GPUs require tens of thousands of parallel threads running at once. It's not because they have that much math to do, it's so they have enough overlapping tasks to hide the agonizing wait from memory.
And that brings us to part 4, why AI types slowly, the grand finale of the memory wall.
Let's tie this microscopic physics lesson directly into the biggest cultural phenomenon of our time, artificial intelligence. To understand AI performance, we look at the roofline model and a super important metric called arithmetic intensity. This is simply the ratio of math operations performed divided by the number of bytes transferred from memory. Imagine a bakery. If you have 100 ovens but only a tiny narrow doorway to bring the dough through, buying more ovens is absolutely not going to help you bake more bread. You are totally limited by movement, the doorway, not by math, the ovens.
Let's see how different workloads handle this bottleneck. A simple scale and add operation does barely any math per byte moved, so it is severely memory bound. A traditional big matrix multiply, which is used a lot in older graphics rendering, well, that does an enormous amount of math for every single piece of data it loads, so it hits the ceiling of the math units. It's what we call math bound. But look at that bottom row. AI text generation only does about 2 operations for every wait it loads. It has a ridiculously tiny arithmetic intensity. It is entirely, hopelessly memory bound. It is quite literally starved for data. Which brings us to the question absolutely everyone asks. Why does ChatGPT, running on actual supercomputers, type its answers to you just one word at a time? Well, picture an AI model as a super fast reader inside a giant library. To generate just a single word, it physically has to run down the aisles and read every single one of its billions of parameters or weights. Then, to generate the very next word, it has to run that exact same lap, reading billions of books all over again.
See, the math to generate the word is almost trivial, microscopic calculations happening on the incredibly fast SRAM inside the chip. The real problem is streaming the weights. It's dragging gigabytes of data through that tiny DRAM memory bottleneck over and over and over again. The slow typing speed you see on your screen, it isn't a stylistic choice. It is literally just a visual meter of the memory bandwidth of the server it's running on. You are watching the memory wall in real time. And this completely explains why all the biggest breakthroughs in AI engineering right now aren't actually about better math. They are purely data movement solutions designed just to hide the weight. First up is quantitation. This shrinks the weights down to 1 byte or less, so there's simply less data to drag through that doorway. Next is batching. This generates words for 100 different users on a single trip to the library, so the data is reused. And finally, flash attention, which cleverly reorganizes the work to keep intermediate scratch data tightly locked inside the fast, on-chip SRAM, completely avoiding the incredibly slow trip to main memory altogether. We've gone from the microscopic physics of a leaky capacitor all the way up to why massive AI systems type the way they do. So here is the big takeaway I want to leave you with today. If you want to really understand computer performance, you have to completely shift your perspective. Stop counting the math operations. Start counting the data movement. Count the distance each byte has to travel and how many you can keep in flight at once. Because at the end of the day, a processor is really just a spectacularly complex machine built to hide the wait for slow, faraway memory.
So next time you see a computer loading, what do you think it's actually waiting for?